So one can create polarized electron beams and even polarized positron beams. They also exist in different laser plasma interactions, situations. So all this is about the plasma and charged particle beams physics. And then, of course, in condensed matter and in nanophysics, you can have ferromagnetic nano-objects where there are very intense internal magnetic fields, which make that also the electron gas present in these objects. The electron gas is also polarized thanks to the presence of these internal magnetic fields. And this gives rise to a lot of phenomena, a large zoology of effects, including spin transport and all the other applications that are related to applicative fields like spintronics that are based on the fact that the electrons carry a spin, and this spin can be used to transport and to manipulate information. So here is a simple standard phase diagram for a quantum plasma, for electrons, for the electron mass. So basically it's a log-log diagram with the density on the horizontal axis and the temperature in Kelvin on the vertical axis. You have different regions of this phase space. And while if you go to high densities and low temperatures, you have a region where quantum effects should play an important role. And this is the region where we are interested in. Although at some point we will also make some semi-classical approximation in order to simplify the model. But you can walk around in these phase diagrams according to the properties of your plasma. Spin and quantum mechanics, well, of course, spin is something that arises naturally in relativistic quantum mechanics from the Dirac equation. Dirac equations, which is based on an object that is four spinors, a spinor with four components, two of which are related to the electronic part and two of which are related to the positronic part. And then each of them, you have the two directions of the spin, and it makes four components. Now, we do not really want to solve the full Dirac equations or something equivalent in the phase space, because we are doing low energy physics. Condensed matter or plasma physics is low energy. We do not want to describe anything like pair creation. It's not the range of energy we are interested in. So we want to get rid of the positronic part of the spinor. And to do this, there's a mathematical tool that is called Foldy Wojtusen transformation, which is basically an expansion in 1/c, which allows you to separate the electronic part and the positronic part in the Dirac four spinor, and then just work with an object which is a two-component Pauli spinor. And this Foldy Wojtusen transformation is actually exact in the case of a free particle. So you can really exactly separate the two parts. When there are electric or magnetic fields, it's not exact, but it's rather an expansion in 1/c. So you can retain terms, you can separate the two components up to a certain order in 1/c, the speed of light, which is of course a small parameter in this case. Now, if you stay at second order in 1/c, you obtain some kind of generalized Schrödinger-Pauli Hamiltonian. The standard Schrödinger-Pauli Hamiltonian, it's zero order in 1/c. And by pursuing the Foldy Wojtusen transformation to second order in 1/c, you get some corrections. So here is the Hamiltonian. You see that the first three terms, well, the first term is just a constant, so it's irrelevant. The other two terms are the standard Schrödinger equation, scalar potential, vector potential. Then the third term is the Zeeman effect, so the interaction of the spin of the particle with an external magnetic field. Sigma is the Pauli matrix. So the first, up to here, that's the standard Schrödinger-Pauli Hamiltonian. And then the rest, you see that all the other terms are proportional to 1/c squared. And so these are second order relativistic corrections. And they have specific names because they are well known. Well, this term is the correction to the mass, the relativistic mass. Then you have this so-called Darwin term, which is a local term here, like this. And then perhaps the most important of them is the so-called spin-orbit coupling, which is known also in atomic physics, the fact that when an electron goes around the nucleus, it has a spin, and since it moves in the Coulomb field of the nucleus, it actually in its own, there's some microphone, in its own reference frame, it sees a magnetic field, and this magnetic field that arises from a Lorentz transformation acts on the spin of the electrons and gives rise to the spin-orbit coupling, a very important effect in condensed matter and nanophysics. So actually the relativistic mass corrections almost always is neglected for a simple reason. Not really physical, but if you look at this, you see that it depends on the P on the momentum to the fourth power. So it would give rise to a Schrödinger equation with fourth order derivatives, which is not a nice feature. So it's neglected, and sometimes one neglects also the Darwin term, although it's not difficult to include it. But we will concentrate on the spin-orbit coupling, or at least I will write down the equations, both hydrodynamic and Vlasov or Wigner for the spin-orbit coupling. Then in practice, in the example that I will show, I will also discard the spin-orbit coupling part and retain only the Zeeman effect as a spin effect. This is because you will see they are very complicated, so they will require substantial numerical effort, but all the basics are there. All the theory of the Wigner and Vlasov theory is there, so one can implement also a practical numerical code to solve this problem with spin-orbit coupling. Now let's move to the phase space, Vlasov and Wigner. Well, if you do the Wigner transform of not of a scalar wave function, but of a Pauli two-component spinor, you obtain that the corresponding Wigner transform is a 2x2 matrix, like the corresponding density matrix is also a 2x2 matrix, written here with the up, down, down, etc. components. Now one can work in this representation. It has some advantages. There are other advantages in changes the basis, working in the so-called Pauli basis by doing simply a linear transformation where the sigmas are the Pauli matrices. And so you move from these 4 components here to still 4 components, but differently. One scalar part, F, that I call F0, which is just the trace of F, and one vector part, F, this one here, which has 3 components, so it makes 4. Now the scalar part is the analog of the Wigner function for a system without spin. So all the properties that are not dependent on the spin will be described by this scalar F0. And then all the properties that are dependent on the spin are described instead by the vector part of the Wigner function, these 3 components here. So it allows to separate just the ordinary mechanical motion, orbital motion in the scalar part, and the spin motion in the vector part. They will be coupled, of course, but it simplifies the notation. And indeed, for instance, so everything that pertains to F0 is in red, and what pertains to F vectorial is in blue. So indeed, so if you take, for instance, velocity moments of the F0 function, you obtain the usual hydrodynamic quantities. For instance, if you integrate it, you obtain just the particle density, the electron density. And instead, if you integrate the vector Wigner function, for instance, the lowest order moment, you get the spin polarization or spin density, so a quantity that relates to the spin, basically the average spin of this electron gas. And so on. I will show later that if you go, it's the same thing if you go to higher order moments. So here it's a reference where some of these things are detailed and discussed at length. Now, so you can write, so once you define with the usual definition, you find, for instance, in this paper, this matrix, the Wigner function, you can write, you can derive a Wigner evolution equation for this matrix Wigner function, either in the standard or in the Pauli representation. This is done also in this paper. It's very complicated. Of course, it's non-local. There are non-local terms as usual in the Wigner evolution equation, but it's even more complicated. So it's if you want to do some practical work, it's difficult. So what we've done here is, and I don't even write it down. You find it in the paper that was mentioned in the previous slide. So what we've done here in order to get something more tractable is to go directly to the semiclassical limit. In the semiclassical limit, well, this spin Wigner equation, what I call spin Wigner equation, will converge to a spin-Vlasov equation, which is written here. Why I call it semiclassical? Well, because by taking this semiclassical limit, actually what we treat classically is the orbital motion of the electron, so just the mechanical standard motion of the electron. But since we still work with this matrix object, the spin degrees of freedom are still treated in a quantum mechanical way. So it's semi-classical in that sense, that the orbital motion is classical, but the spin degrees of freedom are fully quantum variable. So this is these are the four equations for the scalar f0 and for the vector fi, where I is x, y, z, as mentioned before. You see, I put in blue all the terms that are second order in 1 over c squared. So the semi-relativistic corrections that come essentially from the spin-orbit coupling. They come only from the spin-orbit coupling. So it's this term there. And in red here, it's the Zeeman effect, if I'm correct. So then later I will neglect all these blue terms, but as I was mentioning before, the theory is done and one can in principle implement a practical numerical code to solve these full equations. But later I will neglect. Now there's a caveat. Now we've talked about the Vlasov or the Wigner equation, so the equation of motion of the electrons, but we are talking about the plasma or a charged particle beam. So there is some self-consistency. The electrons interact through each other through electromagnetic forces. So you have to couple the Vlasov equations to the Maxwell equations in order to construct a self-consistent mean field model. There is a little bit of a subtlety with that, which this subtlety is dealt here in this Physical Review A paper. The subtlety comes from the Foldy-Votisen transformation, because the Foldy-Votisen transformation allows you you expand the Hamiltonian in order to split the electronic and positonic part, but you have to expand also the wave function in the same way, the Dirac wave function in the same way. And when you do that, you realize that, and you do it correctly, you realize that actually there are some additional terms. So the sources of the density, the charge density, and the charge current get some relativistic corrections compared to the standard expression. Actually, the density remains the same, but the current has a relativistic correction there in 1 over c squared. So you end up introducing a magnetization M and the polarization P, which have to go into the Maxwell equations. One can do this rigorously using a Lagrangian variational approach, as is detailed here. But the end result is that you have some corrections to the Maxwell equation. So that we will also take into account in our treatment. So once you've done that, you have a self-consistent mean field model. And so you can solve the coupled Vlasov, spin-Vlasov, and Maxwell equations as they are written here. And that will be the purpose of the second part of the talk. So I say it again, it's a semi-classical model because the orbital motion of the electron is supposed to be classical, just trajectories, but the spin part of the motion keeps its quantum mechanical nature. Now, there is important thing because that will be related to the method that we use. The above model was based on a 2x2 matrix distribution function in the phase space, in the usual 6-dimensional phase space, that's what I've just said. So this is the wave function, beta and alpha, they go from 1 to 2, so it's a 2x2 matrix, and they depend on the 6 variables of the phase space plus time. Now, some other people, I will mention the paper, I will cite the paper later, have pointed out that one can actually use another representation. Instead of working in the standard 6-dimensional phase space, but with a 2x2 matrix distribution function, one can use alternatively a scalar distribution function, just in the ordinary Wigner or Vlasov theory, but in an extended phase space. And this extended phase space comprises position, velocity, and the spin variable. So it has 8 dimensions, not just 6 dimensions. 8 because it's the 6 dimensions of the ordinary phase space plus 2 dimensions for the spin variable, because the spin variable is a vector on a unit sphere. So it's the 2 angles determine the value of the spin. And one can prove, and it's also in our papers, one can prove that the 2 representations are equivalent, and you can move from one to the other just by taking these integrals like that. So which one to use? Okay, so I showed the evolution equation for G at this scalar distribution function in the extended phase space. Well, maybe it doesn't tell you very much, the equation, because it's complicated, but just to show that it's been derived and it's there. So that there's some deformation of the velocity and deformation of the magnetic field. But if you look, you can establish, so this is one of the papers where this scalar model is derived. And if you do the things accurately, and we've checked, you can prove that the 2 representations are actually equivalent. A little caveat, if the initial conditions are matched by the definition. So if we take our own 2x2 Wigner function and then construct using the correct formula the initial for the initial state, and then construct using this formula the corresponding initial scalar distribution function in the extended phase space, and then we let evolve both F matrix and G scalar, and then they provide the same physical evolution. But of course, they have to be matched. I say this because one could be a little bit surprised that you extend the phase space and the 2 things are equivalent. But they are equivalent only if the initial conditions are matched. One could be surprised because you see that you go from G to F. G is the scalar, and F0 and F vectors are the matrix, through integrals. And one could say, oh, but you lose information by taking integral. Yes, you lose information, but if the initial conditions are matched in this way, then they are still equivalent. But you cannot take anything for G, for instance. So you cannot just take a function of R, V, and S as initial condition. No, it has to come from this expression here, which means that the most fundamental quantity is indeed the matrix Wigner function for the system with spin. Then you can construct the G by basically you embed this matrix distribution function in a larger phase space, but you have to embed it following a specific precise rule, which is this one here. If you fail to do that, you get something that has no meaning. So I'm not sure that it was so clear what I said, but it's important to mention it. So this is the evolution equation. We will use that. I'll come back to that. Now, which representation to use, matrix or scalar? Why? Why choose one or the other? Well, actually, it's quite interesting. You know, there are 2 families of numerical methods to solve the Vlasov equation, called Eulerian and Lagrangian. So Eulerian is like in fluid mechanics. Eulerian means that you have a fixed grid and you solve the Vlasov equation on that grid. Lagrangian means that you have markers, so you have test particles that follows the trajectory, so the characteristics of the Vlasov equations, and so you are like sitting on one of these markers and follow the characteristic of the equation. equation. So this is the base of peak codes, and the one based on the fixed grid, they are often called Eulerian or sometimes semi-Lagrangian. I don't like this, but Eulerian code. So if you think about it for a second, you will realize that actually the matrix representation is better adapted to grid-based codes. Now, grid-based codes are accurate, but they require a lot of memory and time because you have to discretize a very big phase space, 6-dimensional phase space. It's already very big. If you add another 2 dimensions, it's exponential, of course. We've seen this in one of the talks yesterday. You discretize any equation, Schrödinger or Vlasov, you add the dimensions, then the cost grows exponentially. So you certainly don't want to add the dimensions to the phase space, which is already big with 6D. So it's better to use the matrix representation because, okay, you have to solve 4 equations instead of 1. Well, you multiply by 4 your numerical cost. It's not prohibitive, but if you increase the dimensions, you multiply it by 10,000. If you have 100 points per dimension. So that this matrix representation is more adapted to Eulerian codes. On the contrary, the scalar representation is better adapted to particle and cell codes, because for that you don't really matter what is the dimensionality of the space, of the phase space. Instead of having 6 characteristics or 6 variables for each particle, you will have 8 variables for each particle. So it increases a little bit the numerical cost, but it's not prohibitive. So what we have chosen here for the moment, also because peak codes are more flexible and less time consuming, but so I will show, we have developed a peak code with spin effects, and as I said, we've applied it to a specific laser plasma interaction problem, and I will show some results about that. We have also started working on Eulerian codes for the spin plasmas. Actually, we got some results. Actually, in this paper here, actually, we have written down a spin Vlasov code using the matrix representation, but it was a simplified situation, and there is still some work to do. So we are working on both approaches. But here I will talk about scalar representation and the corresponding peak code. Now, a short interlude about hydrodynamic methods. Just 2 slides. Well, once you have the kinetic equations, the Vlasov equation, then you can construct a hydrodynamic model by taking velocity moments. I've already shown. So if you take moments of the scalar distribution function F0, so everything in blue, you obtain the standard fluid quantities. And if you take moments of the vector distribution function in the Pauli representation, so in red here, you obtain all the fluid quantities that relate to the spin, so that were absent in the standard spinless theory. And indeed, what I've already shown, particle density is just the 0th order moment. Spin density is the 0th order moment of the vector, the distribution function. Then the 1st order moment of F0 is the mean velocity. Let's look at the ones in blue. 2nd order moment is the kinetic pressure, where W is the velocity fluctuation. 3rd order moment is the energy flux tensor. And if you do the same for the spin part, for F vectorial, where you get in red here the spin current, which actually is a tensor, the spin pressure, which is the 3rd rank tensor, and so on and so forth. It really allows you to separate the two branches, orbital motion in blue and spin motion in red. And in a very now I show this hydrodynamic equations with spin. It's a 3-moment closure, so we have the density, the spin density, and the mean velocity. I've already made a lot of simplifications here. First, I close. Of course, one needs some rules to close the system of fluid equations. Otherwise, it's an infinite hierarchy. I've already simplified things maximum here, because otherwise they are very complicated. You can find them in this, for instance, in this paper here, the full equations. So I limited myself to 3 moments using a closure obtained using a maximum entropy principle. And the closure equations are this. For the standard pressure, the kinetic pressure, well, it's similar to the pressure for an ideal electron gas. For an ideal electron gas, the pressure is proportional to n to the power 5/3. That comes from the Fermi-Dirac distribution. When you have the spin, you have this modification here, minus s and plus s and blah blah. It's a minor thing. And then an important thing is that we also have a closure. Since we want a 3-moment system, not a 4 or higher order moment, we need a closure on the spin current. This is the spin current tensor. J depends on two indices, I and alpha. And what we write is that it's actually the product, it's a tensor, second rank tensor, that is the product of two one-rank tensors. So the product of two vectors, the velocity times the spin density. So it means that the velocity for an electron, its velocity and its spin direction are statistically independent. Actually, this little assumption here, it's perhaps drastic, but it allows you to make a lot of simplifications in the equations. But you are not obliged to do that if you think. That means that if an electron has a velocity directed in a certain direction, well, its spin direction can be in any other directions without any correlation between the two. Maybe it's not true, it depends on the situation. But it allows to simplify mathematically the equation. So that's the only two slides that I wanted to show on quantum hydrodynamics with spin. Again, here there are no effects in 1 over c squared, so no spin-orbit coupling. Only the Zeeman effect is retained here. Here, the Zeeman effect, interaction of the spin with an external magnetic field. And of course, you would need to couple this to Poisson at least, or Maxwell equation. Now let's move. How long do I have? Sorry, for Chairman.
You have 13 minutes.
13 plus questions.
No, including.
Oh, okay, well, but that's fine. That's fine. I will.
Your choice.
Okay. So applications. So as I said, I used the extended phase-space approach, and we try to construct a peak code, neglecting relativistic terms, so no spin-orbit coupling. So we obtain a non-relativistic semiclassical spin-Vlasov equation like this. There's a caveat. If you looked at the previous equation that I've written before, there was an extra term which contains a gradient in the spin variable, which is neglected here. This is a further approximation, which I don't want to get into. It's also a quantum term, so I don't want to get into this detail. But then you still have this, that's the same, except for this, that's the same spin-Vlasov equation that I was showing before, just written in a more compact notation, coupled to the Maxwell equations, as I was showing before, with the sources that are self-consistent. So the current density and the charge density, they come from the distribution function. And there is this correction that I was mentioning before. So that's the standard current density plus the curl of the magnetization. That was this correction to the sources of the Maxwell equations I was mentioning before. So standard thing, Vlasov equation coupled to Maxwell equations, but with the spin in the extended phase space. Now we simplify things. We suppose, so here is the configuration. You have an electromagnetic wave, laser, that impinges on this plasma with spin. That's why the little arrows. Now we suppose that, so the propagation direction of the wave is along x. We assume that all quantities depend only on this direction of propagation, only on x. And we also assume that the longitudinal field is electrostatic, so it comes from a scalar potential, Ex. On the other hand, the transverse electric field is purely electromagnetic, so it comes from a vector potential, or the vector potential of the wave, that this will be the vector potential of the wave, and this is scalar potential of the plasma. And then finally, we assume another thing, that the plasma is cold in the transverse direction. So we can write the distribution function in this way. It's just an arbitrary distribution in px, in the velocity longitudinal velocity, but in the transverse velocity or transverse momentum, it's a Dirac delta. So this is actually V perp, the argument of the delta function. So that means that there is no velocity dispersion in the transverse direction. So these are the standard actually assumptions to describe laser plasma interactions for Raman scattering. If we do these approximations, then the system can be reduced to, well, these variables here. The phase space becomes 2D, x and px. 2D, well, for the orbital motion plus the spin, of course. So it's here. So, well, we obtain these Vlasov equations coupled to the simplified Maxwell equations with the special geometry that we've just chosen. So there are only derivatives with respect to x and only integral with respect to p, which is px, and s, the spin variable. In blue here, in light blue, I put the terms that are quantum mechanical. And this capital H is a reduced Planck constant, which measures in a non-dimensional way the quantum effects. And these are also all the equations Vlasov and Maxwell have been normalized. So time, that's also standard normalization, time to the inverse of the plasma frequency, momentum to mc, and distance to the ratio of the two, c over omega p, the skin length. So we have developed this geometric Hamiltonian algorithm, which I think that the preprint is already somewhere on archive. But I will not describe this because I don't have time to solve using a PIC code this coupled nonlinear system of equations. So the example that we choose is stimulated Raman scattering, which is a simple thing. You send an incident electromagnetic wave with the frequency and wave number like this, omega 0 and k 0, to an underdense plasma. The density has to be lower than a critical value. And what you get is a scattered electromagnetic wave, Ks, and a plasma wave. A plasma wave Ke that have to satisfy these matching conditions, right? So conservation of energy, conservation of momentum. We use the variable, the parameters that we find in some earlier papers about stimulated Raman scattering without spin, of course. So we've taken these values from the literature, and we study the same effect, including the spin. Initial condition, that's also something to be mentioned. Well, without spin, the initial condition would be like this, so Maxwellian and then perturbed. Now we have to include spin. If you do it correctly, so because you have to do it quantum mechanically, because the spin is a quantum mechanical variable. If you do it with this formula that I showed before that relates the matrix and the scalar representation, you obtain that actually the initial distribution is linear in the spin, in the z component of the spin, because we assume that it's polarized along the z-axis. And eta is the polarization rate, which goes between 0 and 1. So 0 unpolarized and 1 fully polarized. And then, well, you also need to have, of course, a circularly polarized electromagnetic wave to couple to the spin. And you need something that is, the light must also be polarized. And so we choose circularly polarized wave in this way here. So these are the initial conditions, and these are some results. Effect. So E0 is the amplitude of the laser field of the electromagnetic wave. We find so the Raman instability, as we expected. The rate of the instability is proportional to the intensity of the laser, as not the intensity, to the electric field of the laser, as expected as well. So with two values of this field. What is interesting for us is the behavior of the spin. So that's the average of the Z component of the spin. And you see that it starts from a polarized, I think it's eta was 0.5, so half polarized gas, and it loses polarization. And it loses polarization the faster with the faster instability. So the effect of the instability is to move around the electrons and get them interact in a complex way, so that the polarization of the electron gas is lost quite fast, and faster for the case where the instability is also growing in a faster way. effect of the temperature. So here is the previous case, this is just the same figure here, only for longer times. If you increase the temperature, actually you kill the instability, because the thermal effects, they wash out the instability. You don't have any instability anymore, but the loss of polarization is still present. It's actually even faster, but now not because of the instability, but because of the thermal effect. So you have this interplay. If you are at a low temperature, you have an instability that destroys the polarization. If you are at a higher temperature, you don't have an instability, but the polarization is destroyed by the thermal effects. So you have this kind of interplay. Distribution of the spin. So these are the histograms. Horizontal axis is the Z component of the spin, and then the number of spins for each bin. Initially, you see it's linear. I said before, the distribution is linear in SZ. So you have this. And then it starts oscillating. And after several, oscillates like this, in this way, you see it at different times. And after several oscillations, it remains flat. And if you look at the average Z component of the spin, that's the blue curve. And you see that it loses polarization. And these red dots are simply, they point out the different times of these 8 figures, just to show where they are, these snapshots are taken. So you have loss of magnetization. Now in the spin space, so in the 3-dimensional SX, SY, SZ, now we have tried this with the artificial initial condition, which is not the quantum one, it's not the linear one, but just the Dirac delta. All the spins are pointing in the Z direction. This is not admissible quantum mechanically, but we just use it to point out the effect. Otherwise, you don't see anything on the sphere. All the spins, they point to there, they are just pointing vertically in the Z direction. And then you see that after a while, they are distributed almost, not completely, but almost homogeneously on the sphere. And that corresponds to a loss of polarization. If you do that, that was high temperature. If you do the same thing for low temperature, well, it's much less so. You see that it stays much more coherent on the unit sphere. And then you see it also, of course, from the average Z component of the spin, which decays much more slowly. So I finish with that. I spare you the summary because it's just what I've just said. And I just point out this review paper about phase space modeling of solid phase plasmas, where there are large chapters about the spin dynamics. Okay. Thank you for your attention.
So we have 3 minutes for questions. Any questions in the audience? Yeah, Irene. You are muted. You are muted.
Exactly, I am. Yes, yes. No, it's fine. Thank you for the interesting talk. So I wanted to ask whether, like, this 3-moment closure is sufficient in general, or whether you encounter turbulent effects, for example, which in principle would require higher moment closures. And I also wanted to ask in this context, like, is it an alternative to actually model things at the phase space level? So instead of using the hydrodynamic description, like use a lattice-Boltzmann type approach, where I would actually look at the phase space description.
Yes, the first part of your question, I haven't got it. You mentioned some effects, but I didn't, if I have some effects in the equation, but I haven't got it. What was it?
Turbulent effects.
Ah.
Yeah, like
well,
typically,
yes,
which could lead beyond the second moment, yeah.
Yes. Well, we haven't done, you have just written down the equations. I haven't done any practical simulations, so I guess there's no reason. I mean, you have fluid equations. If you put yourself in the appropriate configuration, you can get turbulence. Yes. If you look at the paper that is mentioned here, we also have a 4-moment closure. So as you were saying, in the 4-moment closure, you would have an equation for the pressure, so it would become a compressible. Become a compressible fluid model. Here it's incompressible. Yes, there's nothing preventing you from observing some turbulence if you are in the right conditions. Yes. And well, yes, I agree with you that if I showed you now, as I said, this is already a very simplified closure with this hypothesis, which one should perhaps establish better. But nevertheless, for instance, if I didn't do this closure hypothesis, the equation would be much more complicated. If I go to fourth order closure, they're even more complicated. So I agree with you. I'm not sure that there is a big advantage in using hydrodynamics. And that's why we have done phase space simulation. That's why we have gone directly to the Vlasov equations or to the Wigner equation. Because because it's more complete, it has more effects. It contains Landau damping, for instance. I mean, this damping of the spin that I've shown before, it's a type of Landau damping, which would not be included, of course, in the fluid, in the hydrodynamic models. But there might still be some situations in simplified situations for which one might use the fluid equations. With the Jerome, like the former student of mine, he has worked on this, and he has managed, for instance, to make contact between these models, like this one's here, spin models that we've developed for plasmas, and models that people use in nanophysics, in condensed matters, obtained using very different methods. But then if you start comparing, you realize that basically they contain the same physics. So yeah, so it might also be maybe for analytical purposes a useful approach. Yeah.
Thank you.
Thanks.
Thank you.
We have one more question by Cesare.
Sorry. So these are many particle quantum systems with spin. And very often, in my understanding, these are highly correlated systems. You are using a Vlasov description, which is essentially a mean field description. Can you say, and sorry, maybe you already covered it and I missed it, in which case I apologize. Can you say a little more about the regime of validity of this approximation in this context?
The regime of validity is the usual regime of validity of mean field models for an electron gas. So you have a plasma parameter that has to be small. Now, if I go, for instance, one of the first slides, you see here that there's a classical plasma is on the left of this straight line, solid line, and quantum is on the right. And then you have all this area here, which is named here strongly coupled plasma. So that would be where the mean field approximation is not valid.
So as long as you are towards the right.
Yes.
Okay.
Actually, theoretically, you have to be to the right of this vertical line here.
Okay. That was really my question. Okay.
So it's a bit paradoxical that for gases that obey the Fermi-Dirac distributions, higher densities means more ideal. It's the opposite for classical plasma. So that's why you have to go.
Okay.
Nevertheless, yes, as usual, people. I mean, it would be possible. You can, I mean, still rely on theories like time-dependent density functional theory to modify this Vlasov and Wigner approach that I presented by including some exchange and correlation potentials that in the same spirit of DFT that allow you at least partially to go towards the strongly coupled case. So to include correlations or two-body correlations into the equations and electron exchange effects in the model in the same way that is done in time-dependent DFT, because
yeah, no, but of course DFT then has its own limits, and yeah, no, but yeah, no, I understand the point. Thank you. That was really my question. Thanks.